Welcome back to ECE 441A, 541A. Lab number 1, I hope it's functional. I'm not sure who's done it recently, but I hope that it's still operational. That's due on Monday, that write-up for lab number 1. A week later, homework number 3 is due, which I believe is now available. You may not have quite the background yet, but that's what we'll be talking about a little bit today, is the background material for homework number 3. We're now going to be focusing in the third unit on state space representations, and that will be part of the material that will be covered on exam number 2, which is going to be on us before we know it, the 19th of October. That's another Friday from a few weeks from now. Today what I want to do is talk about another way to find a state space representation, creating another block diagram. We've already said that state space representations are not unique. We can have a different state space representation for the same system. You might have one, somebody else might have another, but they may be equivalent in the sense that input-output wise they look the same. Then we'll talk a little bit about Tier 1, or connecting time domain and frequency domain representations in a scalar case, and then advance into the vector case. And then we'll talk about something maybe you haven't seen before, which is a state transition matrix. How do each of these state variable components evolve in time if we were to, let's say, initialize them at some initial condition vector? How do they now evolve from that starting position or that starting value or set of values? And that will involve a matrix exponential, just as a heads up. Let's now talk about a different way, another way to create a state space representation, and this one is called a phase variable structure. Before we had an input feed forward structure. This block diagram, the way it will be interconnected, will look different structurally. But again, I hope that it provides you with a way to gain some insight into what's happening with the signals in terms of their relationships to one another and how they influence each other between the input and the output. We are starting with the same transfer function. So we're not doing a new system. It's the same third order system. The denominator is monic. We've normalized that leading coefficient to 1. And the strategy now is actually to factor this transfer function representation into two pieces. Instead of just looking at y over u, we are actually going to introduce a new auxiliary variable in between u and y. And that's how we will start then, is we want to now say, let's represent this as not just y over u, but let's now put in a new variable which we'll call w. We haven't changed anything, we've just multiplied by w over w. So we haven't changed anything really, but this now gives us a little bit of a different way to think about this connection of all of these coefficients, a's and b's, in our all-integrator block diagram. And here's how I'm going to now associate these two. So what we've done now is we now have a y over w, and we also have a w over u. And we're going to multiply those together. So now we have two things that we really just had one of before. But what we want to do now is associate these particular transfer functions, y over w with something and w over u with something. And the way that we will do that is we'll essentially pull apart the transfer function into its numerator part and then its fractional part. If we pull off the numerator, there's our numerator. We're going to actually associate that with this transfer relationship between w and y. The other piece, we can't just multiply this by the denominator. We have to maintain that ratio. So the next piece of this is now going to be the ratio with the denominator giving us the information about the dynamics of our system. And this piece, the whole ratio, is now w of s over u of s. All we've done is factored a transfer function and introduced a new variable, w. You could call it whatever you want. I'm just going to call it w of s, to be the output of one and the input to the cascaded piece of that separated transfer function. If we now isolate our attention or focus right now on the rightmost relationship, we can see that we now have w of s over u of s is equal to 1 over s cubed plus a sub 2s squared plus a1s plus a sub 0. And I would like to think that after Monday's discussion, you now have maybe in your mind how you could write that in the time domain. We could cross-multiply, inverse Laplace transform, and I hope that you can now see that this particular transfer function between the input u and this new auxiliary variable w is dynamically connected, where if we take it into the time domain and we have an s cubed times w, what's that correspond to in terms of w of t? Now we differentiate that w 3 times. So we have w triple prime, and I'm going to isolate that on the left side of my equality sign. So I'm doing a few steps here in this arrow, this double arrow. But now all of the other terms that have w differentiated, I'm going to move to the right-hand side. They're going to have negative coefficients or negative factors on their coefficients, so that I now have minus a sub 2 w double prime minus a sub 1 w prime minus a sub 0 w. And I can't forget that I still had that u. And I hope now that you can see a block diagram entering your mind or jumping onto your page connected with that particular third order differential equation. We have w differentiated 3 times, 2 times, 1 time, and no times, and u. And the way to maybe think about this block diagram is to say, oh, in fact, let me go ahead and just treat this as the output of a summing junction. And all of this right-hand side will be the inputs to that summing junction. And give yourself some space, because now what I want to do is from W triple prime, I want to generate W double prime, W prime, and W. And how can I do that? By applying your calculus, right? All we have to do is start integrating. And if I want W out of W triple prime, how many times am I going to need to integrate? 3. So I'm expecting to see 3 integrators really just sequentially connected. And if I now say, oh, here is W triple prime, if I integrate that once, it now produces W double prime. Integrate another time, W prime, and integrate one more time, and I now have W of t. And I can see that I'm actually going to have to get the tape out and extend my page in width in addition to height. I didn't give myself enough space, and I just cautioned you on that. So I can do this a little bit. I can cut and tape a little bit more easily than you might be able to. Sorry, unless you're doing it on your tablet as well. But now that we have all of these W's, I wanted to keep this equation in view as I was doing it. If this now, here is the summing junction that I was referring to before. W triple prime is now coming out of a summing junction, and we want to build up what it equals out of these terms on the right-hand side. And so now I simply have to scale W double prime with minus a sub 2. I scale W prime with minus a sub 1, and scale W with a sub 0 with a negative. And again, I can't forget that input U of t that needs to also be inserted. And there's my all-integrator block diagram that will produce or solve this third-order differential equation. You give me a U and these A's, and I can solve that differential equation through this all-integrator block diagram. But that's not what we want. We want U to Y. Well, we have U to W right now, but if we go back and remember how we defined Y and W, now let's use this first piece and use that to combine the W's into the Y. We now have Y of S over W of S is equal to B sub 2 S squared plus B1 S plus B sub 0. If we cross multiply that with just, or multiply both sides by W of S, now I hope you can see how in the time domain our output is related to derivatives, combination of derivatives of W of t. Or now we can say that Y of t is equal to B sub 2 W double prime of t plus B1 W prime plus B sub 0 W of t. And now these I can add together as the inputs to another summing junction. So these are now inputs. And my output is Y is the output of that additional summing junction, which I'm going to put on the right-hand side. So this is now the output of the right summing junction. Or if I do this in a slightly different color, and now here's where I have to cheat and cut and paste with width. Now I'm going to add in B sub 0 times W to give me one of the pieces. I'm going to pull off W prime, and that point could have been the same place or node that I had before, but I'm just trying not to go through my W prime. This is now B1. And then I have a B sub 2 scaling the second derivative of W. And now I have all of the terms that were on the right side of that most recent output equation formula in terms of weighting with the B's to produce the output Y. And my entire block diagram now, wow, I can even reduce instantly the width of my paper, can't I? With just 2 fingers. It's magic. So now this block diagram that doesn't look like what we had before on the last lecture. The input is now just injected once into this set of 3 integrators interconnected in a different way. And now the outputs of those integrators are being fed forward to produce the actual output Y of t. Questions on where that block diagram or how we produce that block diagram from the same transfer function. Now if I want a state space representation from this, what's the strategy? If I want to now produce or generate or create a state space representation from this block diagram, what's a strategy for making that happen? What's your system matrix going to be dimensionally? Can you tell that just by looking at this block diagram? How big is your A matrix in dimensions? Your capital A. 4 by 4? How big is it? Is it 4 by 4? The system matrix A? What determines the size of that system matrix A? How many state variables you have. And now I haven't yet labeled this diagram as in terms of state variables, have I? How do I create state variables from an all-integrator block diagram? One strategy is just to look at the outputs of each of those integrators and label those as a state variable. And how many outputs of integrator blocks do I have? 3. Now do we want to change our answer on the size of the A matrix? It's going to be square. So if you said 6 by 2, I would have said, okay, where have you been all semester? We know that the A matrix has to be square. So 4 by 4 is reasonable because you see W triple prime, W double prime, W prime, and W. That's 4 things, but we only need 3 of those to give us undifferentiated expressions in our state vector. And the strategy then that we're going to employ is to label the outputs of these integrator blocks as state variables, and let me make that x1 of t. Here is x2 of t, and here is x sub 3 of t. And if those are now x1, x2, and x3, how do I find the derivatives of each of those? Where is the derivative of x sub 1 located?
What if like W triple prime are like fed forward?
So now what if W triple prime is fed forward? Then what do we do? It depends on where it's fed forward. But if it's fed forward inside here, it will just mess up the structure of our state variable description, but it shouldn't cause us any concern, because that's in effect feeding forward U's and W double prime, W prime, and W. Do you see that? So if we fed forward W triple prime, that's equivalent to just feeding forward a combination of the input U and all of the other W's, W double prime, W prime, and W, because those four variables make up W triple prime. Does that make any sense? I have a lot of W's here. Not withdrawals, but W's in a block diagram. Where was I? Oh, I was looking for an answer to the other question, which is, how do I find x1 prime? Where is that? Can you identify that in this block diagram? That answer is so easy that maybe it's hard, right? But all we have to do is walk on the other side of that integrator sign and find W prime, W1, I guess x1 prime, which is W prime. Here is x1 prime. And now do you see how I'm going to actually define, or I need to write all of my primes in terms of unprimed x's and u. And now I have x1 prime and x2 holding hands. They're equal. So x1 prime is just equal to x sub 2 in this way of representing a transfer function or a state space of a system. Here is now x sub 2 prime. And here is x sub 3 prime. And I can now create my state space representation by just applying the fact that the state variables, these x sub 1s, x sub 2s, x sub 3s, state variables are outputs of the integrators. And all I have to do now is look back at my cheat sheet, which is really the block diagram, to fill in all of these holes. I want each of these first derivatives of state variables to be a linear combination of undifferentiated state variables and the input u. And my output equation, y of t, I want to write in terms of combination of state variables and the input. And in this particular set of equations, you should be able to see the system matrix A, the input matrix B, the output matrix C, and the direct feed-through matrix D. Those are staring us in the face if you had to find them. How do I fill in the top row of blanks? X1 prime is equal to X2. That means the only thing that is non-zero here is a coefficient of 1 in the X1 prime equation. And I have zeros everywhere else. Now we can go back to our cheat sheet, which was right here, and say, what's X2 prime? That's similar to what X1 prime was. X2 prime is simply X3. We get some interesting blank fillers in this next one. X3 prime. We now need to write that in terms of some combination or scaled version of our state variables and input. X3 prime is just u of t, so we know that the u comes in with a coefficient of 1. X1 is weighted by minus a sub 0. X2 is weighted by minus a sub 1, and x sub 3 is weighted by minus a sub 2. Questions on the A matrix and the B matrix. The A matrix is 3 by 3. There's 9 entries there, 9 elements in the A matrix. The B matrix, the input matrix, is 3 by 1. The output matrix C is next. How do I create y of t? That one's a little bit more involved than our previous state space representation. Now it is b sub 0 times x1 plus b sub 1 times x2 plus b sub 2 times x3 plus 0. Questions on how we filled that in? And now we should be comfortable simply saying, oh, I could rewrite that as a vector x differentiated. That's now 3 variables buried inside it, stacked on top of each other, equal to an a x of t plus a b u of t, and y of t is c x of t plus d u of t. And we should be able to now fill in the information that's contained in on all 4 of those matrices. The A matrix, the top row was simply 0, 1, 0. The middle row was 0, 0, 1, and the last one had more structure to it. It had our denominator coefficients negated. What about B? It's not too exciting, is it? But you can't forget that it does have a 1. That's where the input is injecting its information, is down, and it's directly impacting x sub 3 prime. But x3 prime, or x3, now impacts x2 prime, and x2 impacts x1 prime. So it's all interconnected because of that superdiagonal set of ones in the system matrix. So all three of your state variables are playing with each other back and forth. What about C and D? Questions on where that came from. And now, if somebody gave you a transfer function g of s that was b2s squared plus b1s plus b sub 0 over s cubed plus a sub 2s squared plus a1s plus a sub 0, do you see how you could say, oh, I can, by inspection, fill in my state space representation? I can now, do you want a phase variable state space representation? If you do, I can just put in the b's where they belong and the a's where they belong, and I have to keep my ones in play, but now I have a third order state space representation immediately from a transfer function description of that system. And you could do the same thing with what we talked about in the last lecture. In the input feed forward, you could go by inspection from the transfer function and populate the A, B, C, and D matrices with the appropriate values in those matrix locations. Questions on that? Now you should be pretty comfortable moving back and forth between these clouds. You're comfortable working with the cloud. Now you have three new clouds. One is a G of S, one's a block diagram, and one's a state space. But you should be able to now, we've already talked in the last couple of periods how to find a block diagram from a G of S. You can, using block diagram algebra or Mason's gain, go the other way from a block diagram to a G of S. You can label the outputs of your integrators in a block diagram to produce a state space representation. From a state space, do you see how if I gave you this and said create an all integrator block diagram, I hope you're okay doing that. You know you need three integrators, and this is how you would label those. You would label the outputs of those integrators as x1, x2, and x3 and interconnected appropriately. You now know how to go that direction. We also now, based on what we've done today, we can go from G of S to a state space by inspection or through derivation. And how do we go here? From state space to G of S. That's our cheer. That's cheer 1. That's one way of doing it. So we could say, give me a cheer, and that says that G of S is now C Si minus A inverse B plus D. And implicit in this diagram is frequency domain and time domain information. Buried in there Your state space representation is a time domain description. Your block diagram could be all integrator. It could be 1 over S expressions in those integrator blocks. G of S is in the frequency domain. What we want to do now is make that connection or relationship between time domain and frequency domain even more, or strengthen it even more. What we want to do now is look at or consider the fact that time and frequency domain representations can be related for linear time invariant systems. What if you had a nonlinear system? You showed me on the exam you know how to deal with nonlinear systems. That was problem 1. You simply linearize, and now you have a linearized version. It's an approximation, and it's good locally around that particular nonlinear operating condition of that system. Let's now start with our training wheels on and look at a scalar case of this connection between time domain and frequency domain. Let's consider a scalar. Time invariant system. And when I say scalar, that really means that we have a 1-by-1 system matrix A. And it's time invariant, which means that if A is now lowercase since it's 1-by-1, and B is a scalar, C is a scalar, and they're time invariant, these are all going to be constants. Or, writing that in a state space representation, I can say, oh, I have x prime of t is a x of t plus b u of t, y of t is equal to c x of t. There's a scalar first order differential equation with constant a, b, and c. And if that was a low pass filter, the A's, B's, and C's might have capital R's and capital C's, capacitors and resistors, in them, giving us the behavior of this low pass filter. What if we Laplace transform that system? What happens when we Laplace transform a derivative? And now I want you to keep track of all of the different pieces or parts. A derivative in the time domain corresponds to what in the frequency domain? Multiplication by s. So now we know that we're at least getting an s, capital X of s. And we want to keep track of everything, so we need to keep track of the initial condition, and that's found by subtracting x at time t equals 0 minus from the derivative of x of t's Laplace transform. What if we Laplace transform the first term on the right of that different dynamic equation? A is a scalar, that's a constant. That can slide outside the Laplace transform, and now we just have capital X of s. Doing the same with the second term, we have the scalar, the constant scalar b sliding out, and we now have b u of s. Let me combine my terms involving capital X. I now have s minus a, capital X of s, equaling x of 0 minus plus b u of s. Just doing algebra in the frequency domain. And at some point I want to connect frequency domain to time domain, so I'm going to want little x of t. But little x of t is buried inside capital X if I simply do an inverse Laplace transform. Let me now solve for capital X of s. And to solve, I can simply divide both sides by this factor s minus a. I now have 1 over s minus a times x of 0 minus plus 1 over s minus a b u of s. What's this look like in the time domain? I have this expression for capital X of s written as a sum of two pieces. And I want to now inverse Laplace transform capital X of s. I can inverse Laplace transform both of those pieces or those two pieces separately. What's the inverse Laplace transform of a constant times 1 over s minus a? And here I will say recall. This should be a recall from an earlier class. And if I had you in ECE 320, you better be able to answer this. What's the inverse Laplace transform of 1 over s minus a? Having a heart attack up here. E to the AT. So this is simply e to the AT. And that we actually call something special. This e to the AT is our state transition matrix. It maybe doesn't look very special because it's a scalar matrix A. Capital A is little a, our system matrix here. Maybe doesn't look like a matrix to you, but that's now a matrix exponential. That's e to the AT. But if I give you a matrix exponential and you go, oh, I don't have any idea what that even looks like or how to think about it, well, just fall back on this and say, oh, I know, I can find an exponential, e to the AT. So if a is negative, what kind of behavior do you have? If I said e to the minus 2t, do you see what that looks like as a function of time? Put in and what have we done here? If I threw away the input, if I could just get rid of that, what would I have? I would now have an initial condition response. I have the initial condition, x of 0 minus times e to the AT in the time domain. That's now just going to be an exponential decay, and that decay is influenced by the value of a. If a is negative, it's well behaved. Now, I need you to recall something more. Part 2, which I had crossed out before, I want to now recover that and say, what's the inverse Laplace transform of that. And if it looks a little bit scary, why don't we take it apart? Why don't we think of this as h of s and this as g of s? Now I have a product of two frequency domain expressions, h of s and g of s. So now if I say, what's the inverse Laplace or if I have h of s and g of s in the frequency domain, what's that correspond to in the time domain? Convolution, everyone's friend, right? So now we have this convolution integral in the time domain, and we could flip and slide. I don't know how you learned this, but anyway, we have h. Let's flip and slide that one. And now we have this time domain expression for these terms. So if I could now inverse Laplace transform h of s, I could then form h of t minus tau. I could find an expression for h in time. If I can inverse Laplace transform g of s, that's not going to be hard, is it? I just hit the shift key to find the Laplace. I just have to unshift it to find the inverse Laplace. So the inverse Laplace of capital U scaled by b is just u of t. But I've just found the inverse Laplace of h of s, have I not? Isn't that just what I did before to get the initial condition response? Man, we're on easy street. So now what do we have? We have the inverse Laplace of 1 over s minus a times b u of s. This we said is a g of s. This is like an h of s. And now we have our form that we can use. We now have this integral from 0 to t. And what was h of t? E to the at. But now we replace t with t minus tau, so we now have e to the a t minus tau. And what was the inverse Laplace of g, capital G of s, or little g of s? That was b u of t, but we're inside the integral, so I'm going to give it an argument of tau, and now I have that expression. I now have a convolution integral Where did that come from? That's if I have an exciting input going into this first order system. If I have a non-zero input, it comes into that system dynamically through this convolution integral in terms of a solution. So that now I can write my result, x of t, as a sum of two parts. X of t is due to an initial condition piece, and it's due to a convolution integral of that matrix exponential with the input, which is now e to the a t minus tau b u of tau d tau. Now in an interview, if somebody gives you a first order differential equation, you can start writing down these convolution integral expressions and really impress your interviewer. Right? You can say, well, that's just a convolution integral for the input piece, and the initial condition piece is just going to be this exponential relationship. Now what we want to do is put on our helmets, take off our training wheels, and go to the vector case. We'll pick up at that point next time.